Welcome back for the second part. In this video, we will talk about concavity, finding points of inflection, and that's going to be example 3 and 4. Okay, example 3 and 4. We did example number 1 and 2 on our first video. Finding critical values using the second derivative test to identify whether it's a relative minimum or maximum. And using those, we also found the increasing or decreasing interval. So example number 1 and 2 and 3 and 4 together will help you to solve your classwork problem for the day. 3.2, this is listed down here. So video part 1 will help you on A and B. And what I'm about to do right now is going to help you on C and D, okay? Alrighty, let's get started. Let's talk about this concavity, okay? It's a great picture right here. Well, let's use this picture right here that I screenshotted. You heard me briefly talking about what concave down looks like. It's like a mouth of a frowny face. Concave down will look like this. And what you will notice is that if you try to draw a tangent line to this curve, notice how the tangent lines will be above your curve. The graph is below your tangent lines. If you look at the slope of this tangent line, notice the slope of this very first tangent line is positive, right? Positive slope. And if you look a little bit to the right, what's the slope of this tangent line? This is zero slope, right? And look at the very last one, this one to the right. Go a little bit to the right. This one has negative slope. What I want you to notice is that starting from positive 0 to negative, concave down is where slope of the tangent line is decreasing. Okay? And we call that concave down part of the graph. Now let's look at the other one, the concave up case. Up, you know, when you get a positive second derivative, the graph will have, for me, it looks like a face that's smiling. But anyways, a concave up graph, if you try to draw your tangent lines, notice this tangent line right there is below this curve. That one right there again, and that one too. So the entire graph will be above its tangent lines. So let's look at these slopes. This slope is from left to right is going down, right? This slope is negative. You go a little bit to the right. This flat line has zero slope, right? And this one, if you go a little bit more to the right, this slope has, well, the slope is positive. So what you notice is that in concave up part of the graph, the slope of the tangent line, or you know what we can say? F prime of x is increasing. So that's what this concave up, concave down is about. But let's organize this a little bit and use that. Well, really, we're going to use that picture idea in when we're doing page 4 and 5. But let's fill out these blanks that I got up here for you. It's called a test for concavity. Suppose that f is a function whose derivative f prime exists at every point in an open interval I. Then f is called concave up on that interval if f prime is increasing over I. Let me draw a picture, okay? So concave up graph looks like this, looks like this, looks like that. If I try to draw a tangent line to this curve, well, tangent line is about, because the slope of the tangent line is this f prime, slope of tangent line. What they are saying is in a part of the graph where the graph is concave up, your slope of the tangent line is going up, increasing. Here's the tangent line, okay? Tangent line, this line right there has a negative slope, right? Negative slope at that point. If I go a little bit to the right, it's slightly less negative. But at that some point, I'm going to have a slope of 0. A little bit to the right, this one right here will have a positive slope. Another one tangent line right there is getting bigger. So slope of the tangent line is getting bigger. And concave up is the graph. When you try to draw all these tangent lines, your graph will be sitting on top of these tangent lines, okay? So that's concave up. And you know how I memorize it? This is what I do. Concave up looks like a little, smiling mouth. And then if you try to draw those tangent lines below it, the graph will be above it. But that's where the slope of the tangent line is increasing. Let's look at the second case, the concave down. Concave down, F is concave down, if the slope is decreasing on this interval. So something like this. It's going to look like this, where you can draw all these tangent lines. Now that one right there, that line has a positive slope. You will agree, right? But if I go a little bit to the right, that's slightly less positive. I should probably make that touch it though. Now that slope is 0, but if you go a little bit more to the right, the slope is now negative. So slope of the tangent line is decreasing if the graph is concave down. Oh no, I forgot to fill out a couple of other blanks. Let me go ahead and go back to this bullet point over here. Sorry. If the second derivative is positive for all x on an open interval, then we just call this graph concave up. So we're talking about slope increasing. So the rate of change of the slope. So that kind of makes sense that we're using the second derivative. And when you are asked to talk about concavity, you will have to use the second derivative, okay? Unless you are specifically asked to use a picture given or graph given. All right, the second one, if the second derivative is negative for all x on an open interval I, then the graph of f is going to be concave down. I hope I'm making sense here. But if I were to highlight a couple important things here, if the second derivative is 0, then it's concave down. And if the second derivative is positive, then we're going to say, hey, the concavity or concave, this graph is going to be concave up there. So remember those two things that I just highlighted. Those two are going to be the important pieces for example 3 and 4. Let's find the points of inflection. What does that mean? Now, back to that one little picture that I had on page 4. Notice how concavity changed from left to right, right? So this was concave down. And then at that point right there, this point right there, it started being concave up. So it's called point of inflection. Okay? Is where the concavity changes, okay? Now notice for concave down, the second derivative is negative, right? And for the concave up case, the second derivative is positive. So what do you think is the second derivative at the point of inflection? What's in between anything negative and anything positive? Well, the point of inflection will be the point where the second derivative is equal to 0. So let's fill that out and let's find some of these. Okay, f has a point of inflection and must occur at a value x naught or x of 0 in the domain of f if where the second derivative is equal to 0 or where it doesn't exist. And in our class today, in our lesson today, I'm just going to ask you to focus on this piece in all our polynomial graphs. And maybe we get to talk more about the other case in another lesson. But for right now, I'm going to go with that grade box section right here. So what we just talked about in the last couple minutes. What I highlighted in red, blue, and green, the gray, these are going to be the big important ideas, okay? So let's use that on example 3 and 4. And as we go over these examples, things will make more sense, okay? All right, example 3. For the following function, and you've seen this guy before, where did this come from? This is our example 1. For the following function, A, give coordinates of any points of inflection. Okay, so we're going to find that first. Identify B, identify intervals where the function is concave up or concave down. All righty, you ready? So in order for you to find any point of inflection, A, points of inflection, what you're going to do is you're going to have to find the second derivative. You're going to have to find the second derivative, and what do? You set it equal to 0. Okay, so let's do that. The first derivative is going to be 3x squared plus 6x minus 9. Remember, we found that before. And in fact, I think we also find the second derivative to use the second derivative test. But let's find it one more time. That's going to be what? 6x plus 6. Now, to find the point of inflection, what do? You set this second derivative equal to 0. 0 equals 6x plus 6. Now, let's solve this for x. Negative 6 equals 6x. Therefore, our first, I'm going to say a potential point of inflection. We're not going to be able to say, hey, this is a point of inflection right now. Because I think, okay, I should probably read this with you. If it has a point of inflection, then it's going to happen at that point. But we're not really sure yet. So don't call this point of inflection yet. Just like how we find critical values, but we never call them relative minimum or maximum yet until we find the signs to the left of it and to the right of it. So what you're going to do is just kind of circle that number for right now, but we're going to go to B first. We're going to do the intervals where it's going to be concave up and concave down. And if it's different to the left and right of it, then we get to say it's a point of inflection. But until then, don't call this a point of inflection just yet, okay? Let's try part B. So just use that number. I'm going to do the part B right here. So put the number -1 in your number line. And in order for you to find where the function is concave up or concave down, you will need to use your second derivative, which is f double prime of x equals 6x plus 6. So it's very similar to your first derivative test. You plug in a value that's to the left of -1 into your second derivative. Let me plug in -2. 6 times -2 plus 6. That's going to be -12 plus 6. What I got is a negative number. If second derivative comes out to be negative, what do we know? This is going to be a section where the graph is concave down. So this is going to be concave down to the left of -1. Now we're going to find the right side. Let's plug in f double prime of a number that's greater than -1. I'm going to plug in 0. 6 times 0 plus 6. That's going to be 0 plus 6, 6. So notice this is a positive number. Positive second derivative implies this section is going to be concave up. Okay, so this will be concave up. Stop. Go that way. Then notice how concavity changed to the... Stop and go that way. I'm sorry, my dog is just scratching the furniture. Now, okay, so when the concavity changed to the left and right of it, then we get to say this point right there is a point of inflection. So I will say concave down on -infinity to -1 and concave up on -1 to positive infinity. And we have a point of inflection at -1. What's the y value? We better find that y value, right? Let's find that y value when x is -1. So where do you plug that -1 in? Into the original function. -1 cubed plus 3 times -1 squared minus 9 times -1 minus 13. That will be -1 plus 3 plus 9 minus 13. So what's that going to be? -1 plus 3 plus 9 minus 13 is -2. So the inflection point is at -1, -2, and we answered this question completely. So that's it. That's what we do. Let me box my answers. I think it's a little bit easier than the first two examples. Well, let's try one more. Okay? Down here. Find any relative extrema, any point of inflection, and intervals where the function is concave up or down. Now, do take this part out for me. We already found relative extrema for this function on example 3. We did. I meant to take that out. And call this A and call this B for me. Okay, we did all the extrema and increasing, decreasing interval on our first video with these exact same functions. I want to focus on the point of inflection and intervals where this is concave up or down. So let's try. Let's find point or potential points of inflection. Maybe points. First, find G prime. G prime is 20x to the third power plus 60x squared, right? Take the derivative of the original function, and that's good. G double prime, because in order for you to find concavity and point of inflection, you need the second derivative. That's going to be 60x squared plus 120x. And what do? You set this equal to 0. You know, while I'm here, let me go ahead and factor out the greatest common factor. They're both divisible by 60x, and I'm left with 60. X plus 2 in there. So I got 2 points. X equals 0, or x equals -2. Can I call these 2 points of inflection yet? Not yet, until you check the concavity to the left and right of these 2 points. Okay, so I'm going to move on to A without calling any of these point of inflection yet. On number line, -2's here, 0's right here, and your second derivative function, keep saying f. Not f, but this guy is g. G double prime is 60x squared plus 120x. So let's plug in something to the left of -2. What is G double prime of -3? That's going to be 60 times -3 squared plus 120 times -3. Let's get the sign of that number. 60 times -3 squared plus 120 times -3 is 180. This is positive. So what do you say? The second derivative came out to be positive. This must be concave up. All right, let's check the region in the middle. The region in the middle, I should be able to plug in G double prime of -1. Because -1 is in between -2 and 0. If I plug in -1, I'll get 60 times -1 squared plus 120 times -1. So that's going to be -60. This is a negative number. Negative second derivative means that this interval that I just checked is going to be concave down. All right. So guess what we know? -2 must be the x value of a point of inflection. Let's keep going. Let me just find the other one. just keep changing these colors. Plug in G double prime of 1. That's going to be 60 times 1 squared plus 120 times 1. And without a doubt, that's going to come out to be positive, isn't it? That's going to be a positive number. So this is going to be concave up. So I checked all those, and I'm noticing that -2, the concavity to the left and right is different. 0 to the left and right, that's different. So guess what? These two are both points of inflections. Yay! So you have to check that, because maybe the concavity doesn't change, then you don't get to call them point of inflection, okay? So let me write my answers, okay? So concave up on -infinity to -2 and 0 to positive infinity. Concave down on -2 to 0. And we have 2 points of inflection. Points of inflection at. Now, I only have the x values. Guess what? I now need to plug in these x values into the original function to find the y values, right? So let's do that. So what is g of 0? That's going to be 5 times 0 to the 4th plus 20 times 0 cubed. And nicely, that is going to be 0. So the first point of inflection is at 0, 0. The second one is going to be at where the x is -2. So I'm plugging them into the original function. 5 times -2 to the 4th plus 20 times -2 cubed. And I need the exact value. So let me type this in. 5 times -2 to the 4th plus 20 times -2 to the 3rd power. I got -80. So the y value is going to be -80. So we got it all. Let's go ahead and just box this answer. So in this video, we talked about how to find concave up or concave down intervals and how to find the point of inflections, okay? So that looks great. This is a good stopping point. I will come back and go over the sketching graphs and reading graph in our very last video. But you are really ready to start on your 3.2 problems, okay? Well,